20 or so microns, simply because the reference position was assigned basically just as a visual inspection.
I see.
But all that's going to affect is if you do if you do like a percentage strain, that's all it's going to affect. So.
And do you need to do dye again, like 0 or something, 0 force actuator, you said?
Well, once the actuator is once you've set the 0 position, that number is coded. It's hard coded until you change it.
Okay.
So until you do that procedure again. So you shouldn't need to do the center position unless you change the load cells. And as far as frequency of load cell calibration goes, we don't really have a spec for that. Theoretically, as long as you haven't changed them, the calibration factor shouldn't change at all. But over time, due to like even if you had, a temperature change in the room, it might affect it a small amount. So I would suggest that if you're at the beginning of a study, at the beginning of doing a bunch of test samples, it would be useful to reassure yourself and do a load cell calibration. But theoretically, it shouldn't change again as long as you haven't changed them. So before we load it, I'll just 0 the load cells, because that's the one thing that can drift a little bit just due to temperature changes in the room. The calibration factor won't change, but the 0 can change very slightly.
So before you mount the sample to
Yeah.
the racks.
So I'm just going to raise that up a little higher. So I want to be able to, I'm just going to bring, okay, so our lights weren't in very good position there before. So we can see the sample in the field of view of the camera. So you want to leave a bit of an apron around the edge of the sample and get it as centered as possible. And then you can just raise it up until it's making contact and the rakes are sort of slightly bent. And as far as balancing the forces in each axis, it's best to try and puncture through all the points at once using, just a flat surface or a little cube like this. So I'll just go and push all those through. And if you need to, you can go through and just touch it up a little bit with the flat edge of a screwdriver or something. I'm just going to make sure those are all punctured all the way through. Okay. So I'll just very gently lower that down. You can see it's still adhering a little bit. So you just want to very gently peel the backing material away from the sample. Sometimes it'll stick, sometimes it's useful even to put like a wetted Kim wipe or something on the back, so because this backing material can be quite sticky, and sometimes it can take the sample with it, so you need some buffer between them to make sure it peels away evenly. So the focus on this camera is quite sensitive, so I'm just going to make sure that we're focused right on the sample.
So this would be about the right field of interest?
I'm just going to back it off a little bit, simply because you can see that it's a 1280 by 960 array of pixels, so we have a bit less room vertically than side to side, so I'm just going to have to back that off just a little bit and refocus it. There, that's probably a better size.
So how big is typical for this typical sample? Like 5 by 5?
It's about 6 by 6 actually,
Okay.
because including the apron around the edge,
Yes,
because
yes.
you want to find a balance. Typically in biaxial testing, you want to find a balance between, you want a bit of an edge around it so that you don't tear right through, but the larger the apron around the edge is, the more it's also going to affect your force measurements.
Yes.
So we actually have a white paper you can refer to that gives some rough guidelines about what edge you want in a biaxial test. So you can see when we punctured through. So we punctured through, and we kind of punctured down, and when we punctured through, they kind of punctured down and away. and then we peel the backing material away, they actually spring back inward a little bit. So we have a bit of a negative force on each axis. But we can correct that with a preload. So I'm just going to check something here. This is something maybe we'll cover at the end of today or tomorrow. But if you want to move to force, there's a set of control parameters that govern that movement. And those need to be set correctly to achieve force precisely and in a short amount of time. But I can get further into that later.
So it's the force or the corresponding stresses?
Well, the force and and the stress would be analogous
Right.
to that. So.
Okay. Yeah. Okay.
So we have a number of different test functions you can use. So you can name each set in the test sequence. So for the first test, we have a number of different control modes available: displacement or force control. So under displacement, you can do a ramp function, which is it's analogous to engineering strain. You can do a true strain function. So that'll be a nonlinear function increasing its speed as the sample gets bigger. And you can also do a sinusoidal function. And it'll approximate a sinusoidal motion as it stretches and contracts. But just for now, I'll say we can probably do, I don't know, like a 20% stretch. And you can assign the stretch magnitude in either percent.
These are the profiles.
Yeah.
Different profiles. The RAM. No, the RAM. The true strain.
So you can assign the magnitude either in terms of percent stretch. So and as using so if you use percent in ramp, it would do engineering stress. If you engineering strain, if you use true strain, that percent will be the true strain calculation for percentage.
Okay.
Or you can specify it in micrometers. So for now, I'll just do 20%. So if we're 4,800 by 4,800, let me see, that's 4.8. That's 960 micrometers of motion. There's a handy button here if you just want to do the same thing in both axes. You can just hit same as X. Now, to reduce the slack and get some known starting position, you can also apply a preload. So typically, you could do 0 force for a preload, but typically it's good to have some small value for your preload, and it gives you a defined starting point for your test. So for this, I'll say, I'll just do 25 millinewtons. So what it'll do here is do force control and move it to 25 millinewtons in each axis. It'll recalculate the strain based on the size after the preload has been achieved, and then execute that strain. So you can assign a stretch duration, a hold duration, so when it pauses at the top of the ramp of the displacement, recovery duration, and you can also assign a rest duration, so a pause at the bottom of the displacement profile. You can also do not stretch or do not recover. So if you wanted to do like a 10% strain followed by a 20% strain based on that size, you could skip the recovery on the first.
So recovery means the unloading?
The unloading.
Okay.
Yeah.
Okay.
You can choose the number of repetitions for each set and the data output frequency. So the force and displacement data can be output up to 100 hertz, and the maximum image output frequency is up to 15 hertz. So maybe like a typical test might be like a preconditioning set followed by a test set. So you can insert multiple sets in a test sequence. So if I just click insert below, it'll copy the test set that I currently have highlighted. So say our test set only has one repetition after the preconditioner. And then you can reapply preload in each successive test, or you can even reapply preload after each repetition within a set. So once we're happy with the setup, if we had fluid, if we were doing an aqueous test, you can just raise that up until it's immersed. And
cause any trouble for the strain measurement, either the PBS or any other solution, or do we need to have different colors?
it may distort it a little bit, but we did come up with a solution for that. So the water can create a bit of a shimmer and distort the image a little bit. The other problem is that if you have some contrast agent like graphite on the surface of a sample, it can kind of float up off the sample and be drifting around during the test. But that can be mitigated just by, once it's in place, putting a little glass slide in place. So the solution in there will wet up to the surface of the slide and it'll draw any particulate away to the edges, and also have sort of a consistent focal plane for to look at through the test. So I'm actually just going to darken that up a bit. That's a little bit bright. That looks a little better. And having the glass in place actually did affect the focus ever so slightly. As you can see, there's actually a little spot on the surface of the lens, or the surface of the slide. So that's just a standard 3x1 microscope slide. So I would say that's still a little too bright, so I'm just going to bring that down even further. Okay, that looks good. So once we're happy, we can press start, and the sequence will run through automatically from the start to the end. Okay, so this little dialog here, we have the temperature set to 37, and we're below 37. So it just does a double check, and you can disable that if you don't want it to come up with that. So.
So three different windows are, well, yeah, first time displacement versus time, and first versus displacement. So the first cycle would be just preconditioning, or first 10?
However many it requires. I mean, sometimes you don't need preconditioning. It really depends on the material that you're using. But I know it's a often used kind of feature of biaxial testing that preconditioning is actually necessary.
Typically for the biomaterials, so tissues, and we do have this kind of thing. So it goes up to about 0.6 to 2. But suppose if we don't do any testing before for certain materials, how can we know, amount of displacement or forces we have to apply?
Well, you can do some preliminary testing on a sample and get an idea of the kind of ballpark range you're working in.
Right. Yeah.
And we also have a force control method you can use that it doesn't work quite as neatly as in terms of getting a linear profile, but there is a way to do it. So once a test is finished, everything on the screen is frozen, and you need to go and do a new collect new to be able to proceed any further.
So this one is the second, the test one.
So you can see we have a bit of a higher force peak because we did the preconditioning, and then after that, the bottom of the force profile is going below 0, and we did another preconditioning or another preload before we began this test, and it recalculated the strain after that preload again, so we had a slightly higher peak.
So the typical output will be, based on this measurement, will be force versus displacement. Okay. So, but if we want to integrate further with the strain measurement, then that would be an additional thing.
Yeah. You would go and do the analyze and review, do a surface strain protocol. That you can output the strains in a format where you can just easily cut and paste from this. It time correlates the data being captured for force and displacement, and time correlates the images. So once you get that data, you can easily cut and paste those columns right into the same spreadsheet. All the data is in CSV files, so it's well suited to Excel and MATLAB and those types of software
So you have to
packages.
save the files, data, or anything, or it's already saved in that particular folder.
So the data from this test will have been saved. And one thing I'll mention also, if you want to prematurely end a test, there is a stop button here.
Oh, okay.
So if the test isn't proceeding as you intended, you can actually stop it, and it'll move right to its shutdown sequence.
Okay.
But if you have a stop a test, it's better to do that than just to shut the machine off, because you can more easily recover from a software shutdown than just powering it off. Because if you power it off in the middle of a test, the actuator position won't be properly stored, and you'll have to reset the actuators to
Okay.
bring it back to its reference position. So the data should be in C, cell scale, LabJoy data. Let me see, test 004. So the data that's recorded, this is all the images from the test. And I'll just go top to bottom here. So there's a log folder where everything that was written to the log window here is also written to a notepad file. If you ever have difficulty with the test, or you're having some, if there's something we need to debug, sometimes it's useful to see that if you need our help, or technical help for something. There's also a tracking folder where once you've done tracking, all the tracking data will be saved to that folder. All the images captured from a test. There's a .tst file here, which what the .tst file is basically a record of the images and how they correlate to the data that was recorded for force and displacement. So when you do an analyze and review, it's going to refer to that file to be able to time correlate everything when you're reviewing them. And the force and displacement data is just recorded in a CSV. Okay. So it's just in a CSV in a neat column format. So the hierarchy is, goes from top to bottom, from set name to the cycle in that set. Time. It does record the temperature in case that's pertinent information. So X size and Y size. So that's the actual size of the sample or the actual separation of the rakes at any point in the test, and also X displacement and Y displacement. So the difference between X displacement and X size is that X displacement it's set back to 0 at the beginning of each cycle and after a preload is achieved. So once we're done the preload here, let me see, preload, it went to 72 micrometers and then went back to 0 again. And then the force and the force data. So I'll just go through, let's just have a look at that. Look at our force data as well. Okay, so we captured data at 10 hertz here, so we can see it's going up to every 10th of a second. And after the first test, it actually, it won't go, after the first test here, you see it went from 10.8 to 10.81. That's actually to be expected because all the data is captured at 100 hertz on board the biotester here. And when it transitions from one phase of a cycle to another phase, it'll grab the next data point at 100 hertz and then start counting up again every 10th of a second. So don't let that worry you.
Okay. Yep. All right. So, let's see.